Hello and welcome to Live from the Lab. This is the show where we talk about different technologies that Brooker has worked on in order to help scientists around the world make discoveries. Now in today's episode, we're going to talk about residual stress. Now when you take a material and you apply a load, well, that load is the stress. And its natural response is to stretch a little bit or create what's called a strain. Now in the beginning, when you first start applying that load, what happens is typically a linear relationship. That is, we're just kind of squishing the atoms a little bit or pulling them out a little bit. Now that response is completely reversible. If you remove the load, it's going to go right back to its original state. Well, what happens if you cold work that material? What happens if we heat treat it or we quench the material? Well, then we're going to trap some of that energy. We're going to trap some of that stress in there. In one way, that's putting us a little bit closer to complete failure of the material. But in another way, we're actually reinforcing it. We're going to have it resistant to fatigue and last longer. So residual stress is actually a really, really important thing. And we're finding not only in the traditional field of metallurgy, but also in ceramics and other modern materials. So to learn more about residual stress and how you actually perform the analysis, we're going to head on over to the table and talk with one of my colleagues. Hey, Jonathan.
Hey, John. How's it going? Thanks for having me.
Wonderful. Yeah, welcome to Live from the Lab, and thanks to everybody out there joining us today. So today we're going to talk about residual stress.
That's right.
So are you feeling stressed today?
Man, I've been so stressed out this whole morning. You know, we have this episode to air. I wanted to make sure everything was going to go perfect.
Yeah, well, let's relieve some of that stress. Let's get on with the show, as they say, right? And
that's
just
right.
Kind of like, hopefully we don't break a leg, right?
Yeah,
Push it past the fracture point.
That's right, exactly. You never know. But so, like you said up there with residual stress, what we're really measuring is strain and then converting that into a stress, right? And this has kind of been one of those pervasive things where it's been really important to get a good characterization of the stress in all these different engineering materials that you see out there to prevent catastrophic failure and things like that. So.
Okay, so now when we talk about the sample itself, let's say in the ideal sense, what is our ideal sample for this type of residual stress by XRD analysis? What is that ideal sample, or a classic example?
It could be a metal, like you said up there, typically a polycrystalline material, right? Because we're going to be measuring the stress in all different directions to get an idea of what the stress tensor is.
Okay, and when we say polycrystalline, that just means it's kind of like sand on a beach. We want to have, if you actually looked at the microstructure, there are millions and billions of grains, and they're pointing in every possible direction.
Exactly.
Okay, and then each of those grains, right, it actually acts like a strain gauge.
Yep.
Right. All right, so now with XRD, though, we can actually unlock that strain gauge. We can read it, right?
Exactly. So the idea essentially behind the measurement technique is kind of similar to a pull figure, when you're looking at texture, but instead of looking at the change in intensity as a function of sample orientation relative to the diffraction vector, what we're looking at instead is the change in despacing.
All right.
So the compression, relative compression or expansion of those crystallites in different directions.
All right, so we're going to have that sample sitting here, and then we would love to measure the stress directly in the plane, because that's generally where it's going to be, but we can't, because you can't come in and out of the same direction. So we're going to make different measurements at different angles, right?
Exactly.
Okay, and the tilt, we call that angle...
We call it psi or chi.
Psi or chi. Yeah, chi is normally like when we talk about the actual machine, like there's a chi
Right, yeah,
circle.
if you have a stage that can tilt the sample out of the diffraction plane, we call that chi or psi. But there's also another way to do the measurement. If you don't have a tilting stage and you have like a theta-theta goniometer, where you can actually change the incoming angle of incidence to basically simulate sample tilt. Right?
Okay, so in that sense, we'd have the incident angle, so the beam is coming in, and then the one coming out, we look at the middle of that, and you can tilt that, or bias it, right?
Yep.
You either do that with the arms, or you do that with the sample.
Yep, and again, you're looking at typically a fixed 2 theta. Right, so the one reflection of the crystal that you're interested in, and just modulating that tilt angle. Yeah.
So I guess if we think about it then, what kind of machine do we need here? Sounds like a pretty basic machine. You just need to have the arms be able to move, or the sample to be able to move.
Yeah, so I mean, it can be basic, or it can be, kind of more complicated. It depends on, what kind of measurements you're doing, what kind of samples you're looking at. And, when we're talking about what I would want in a system, typically a mirror
Yep.
right? If we want to do a line beam or a point beam, you can use a set of collimators to get a point down to a point beam. I like to have the tilt stage. This way I don't have to move my 2 theta, my theta drives. And a nice big 2D detector.
Okay. But you can do it with just a point detector.
You can,
or
yes.
a line detector. You can do a scan. Yeah, I think for me, I think the configuration I really like, though, is generally like a point focus tube and then a set of just pinhole slits. Because then I can change my radiation. I can go copper if I want. If I'm going to measure steel, I can throw in a chrome tube. And that'll just give me a nice, say, like 1 millimeter size beam. Stage, like you said, I tend to like also the side inclination. So
yes,
yeah, that's what we call it when we tilt.
Exactly.
To get different size. And then 5 stage, so rotating.
Yep.
Then you can get stress in all directions.
Exactly.
And yeah, I mean the 2D detectors, especially they're more affordable these days. So you get the smaller one. It gives you still that debayering, much faster results.
Yep.
But if you can't get a 2D, 1D detector.
Yeah, that'll be perfectly fine.
Pretty good.
And you did touch on the radiation a little bit. I think that's also an important thing.
So yeah, why would we? Why would we do it? Copper these days, generally XRD machine, it's going to be copper.
Yeah, right. When you want to compare to all the other people doing XRD out there, copper is like the go-to, right? You think, the universal standard when it comes to radiation. But when you're looking at steels, right, copper can be an issue not only because of fluorescence in the sample, but the fluorescence is a result of the absorption, essentially.
Yeah, that's true. Energy, right? Conservation, right? So it comes in, it's got to do something. It's not going to be reflected out.
That's
fluorescence.
Right. Yeah. So with chrome, it's kind of become the alternative for looking at iron-based materials relative to copper because it avoids that fluorescence, right? Yep. And it also penetrates deeper into the sample because you don't have the absorption effects. Like
gives you penetration depth, and then it also shifts the peaks a bit, right?
That's another thing, right? Excellent point. So obviously with the longer wavelengths, our peaks are going to be shifted out, and there's a really nice iron alpha, believe 211 reflection at like 150 degrees. And the higher angles for stress measurements is preferred because that gives us more sensitivity in our despacing measurement.
Yeah, and that's one of those, blessing and a curse with iron, especially ferrite. It's simple unit cell, so you don't get a lot of reflections. They're bright, but you don't get a lot of them.
Yep.
Man, so the fact that you can shift that peak up to, what is it, like
155, something like that?
Yeah, and that really helps you out. It's all lambda equals 2d sine theta, right?
That's it. Yeah, at the end of the day, it's just Bragg's law.
So a very small shift of the d-spacing yields a very large theta change. And, that's going to be the high angle. So you have kind of like a rule of thumb that you go by? Like I want to have a peak over...
Well, I would typically go for the highest order reflections that I can, or highest angle reflections that I can. That's normally what I would do. But again, you have to kind of use what you have available also, right? Yeah. But maybe that would help justify, maybe I do need to change my radiation to get better results on this sample or something like that,
Yeah, for me, it's always 100. I want that peak to be over 102 theta. And if you do, you're going to get some good results. Below that, they're results.
Right.
You're going to get a number.
The reliability of those results becomes questionable.
Yeah. And the other thing to think about, too, is that we want to have nice isolated peaks.
Yes.
You want to have, a nice peak, not a lot of convolution. Things like that.
Yeah.
All right. So with that, we're going to actually start taking a look at how you'd actually execute a measurement like this. So with our machines, we have this mantra. It's plan, measure, analyze. So we'll start out with planning, right?
That's right. So I have kind of put together some screenshots of how you'd go about the planning process in our software to put together a residual stress experiment for an iron-based sample in this case, and changing the planning parameters or the experimental parameters to extract different stress components in our stress tensor.
Okay, and this is found in which software?
So this is our Diffract.wizard software.
Okay, so it's in Commander.
Yes.
Right, so it's a tab in Commander. You just go in there, press that button, and then you can choose.
And then there's a nice drop-down list. You say, it asks you what kind of experiment you want to run today, and you just say stress,
texture, and then high resolution powder.
And then you'll come to this little window here.
Okay.
And you can kind of see, I just fast forwarded into the stress basic window. We're doing classic stress, in this case, looking at a 1D or 0D example.
Okay.
So just kind of the general workflow of this is going to be determine what kind of collection mode. If you have enough range on your detector or coverage on your detector to do a snapshot, that's great. If not, you might have to do a scan. You have both options available. It makes it really easy.
So before you do this, you might want to do just a scan, see how wide the peak is, and then
always recommended, yeah, to get an idea of what you're looking at before you go ahead and actually plan an experiment like this, definitely. But once you if you're looking at the same thing over and over again, you can just pop this right into your start jobs. If you just want to change out the sample, you know, it's similar. Go ahead and run the same experiment over and over again without any real user input. It makes it very easy.
Yeah, okay.
Next step is to set our 2 theta to the applicable crystal reflection based on what you were just saying. You know, kind of have an idea of what we're looking for, you know, before we go ahead and plan this.
So either know that from doing previous scan, or maybe you looked it up in the database.
Yep, do a test scan to see how long your frames need to be, things like that, exactly. The next step would be to add collection points for sample tilt. And this is, again, our psi angle or our omega angle, depending on how you're doing this experiment. You can kind of see how what we're really looking at when we're kind of doing the strain experiment or stress experiment is we're looking at what we call sine squared psi, which is an approach that uses a linear regression, right? So that allows us to plot the data in such a way that it's a linear, right? And the slope is actually proportional to the stress.
Yeah, I mean, when they kind of developed this method, some of the assumption with XRD was thin penetration depth, right?
Yep.
So we're looking at the skin, and therefore the stress should mostly be in the surface.
That's right. Yep.
And so what we're doing is we're kind of extrapolating that stress as we tilt out of the surface. And what they found is that relationship as a function of angle goes as a sine squared.
Yep.
So sine squared, that's how you want to step them.
Yeah.
The angles. You don't want to go 0, 15, 30, 45, 60.
Yep.
No. You want to do it in
equal
sine squared
steps in sine squared space, exactly. But you have, it's IT always getting in our way.
They want you to reboot.
Yeah.
All right.
But you have kind of the option whether or not you want to step in psi or sine squared. And then lastly, our add data collection points for sample rotation to get us our in-plane relationships. And you can see our full stress tensor is going to be a 9-component matrix. Really 6 components if you consider the shear components are equal and opposite.
All right, so if we assume that we have a uniform stress in the plane, say the sample is like this table, you have a uniform stress in all directions, all you really have to do, though, is measure one set of tilts in one direction.
Yeah.
Right? Then if we assume that the stress isn't necessarily right in the plane, little inclinated relative, and we call that shear.
Yep.
So now we got to measure going one way, we got to measure going the other way, right? Or over the top, whatever you want to do. So
a really good picture version or example, we'll say a visual aid of that would be this.
Yep.
So this is kind of your uniaxial with shear, exactly what you were describing.
Okay, so that's going to be, if you're going over the top, you're not necessarily assuming it's only in the plane.
Right.
But also it might be a little inclinated.
Yeah. So, and one thing that I'd like to mention, the back of the cube is shaded blue. Just, again, you know, some people might see that as the front face, but just want to make that clear.
Okay.
And you can kind of see how the stress components, I tried to make the axis similar to the axis on the measurement wizard.
Yeah.
Right?
Yeah.
When I was making that. So it helps hopefully make it a little easier to understand.
All right, so the circle in the background that we're seeing, that is going to be, that's kind of phi goes around the circle. So that's rotate the sample that goes around the circle.
Exactly.
And then the middle of the circle would be the machine is set up so we're measuring straight out. And then if we were to get to the edge, we'd be measuring right in the plane.
Yep.
Okay.
Yep.
And each dot represents a different
tilt
kind
angle.
Of tilt of that diffracting condition.
Exactly.
Okay.
All right, so if we wanted to add to this and add more components into our tensor, then we would simply rotate the sample 90 degrees to get a kind of what I'm calling a pseudo biaxial with shear. So you can see the added stress components that we'll be able to access. But we still don't have that sigma 1, 2, sigma 2, 1. To get that, we would just do another measurement at 45 degrees in between.
Yeah, I know we used to do that, especially when we didn't have access to the phi stage, or if you had a really, really big, heavy sample. then you could just manually turn the sample 90 degrees, measure it, and you're going to get the stress this way, you're going to get it this way, right? And because you're going over the top again, so you're going to get the shears in both directions. But you don't get that, what happens if the stress isn't right along that axis?
Yes, that's a great point.
And that's where this biaxial shear helps.
Getting the full tensor is going to give you the most complete picture of your sample. Because again, what we're doing is we're just picking arbitrary, you put your sample down. The stress that we're measuring is kind of arbitrary unless you build the full picture. And then you can actually, what we'll see in the analysis is that we can build an orientation matrix and actually look at, okay, what are my principal stresses? Which is based on a series of, a system of equations that's used to calculate that.
And that's one of the nice things about this method is that it can be used on a very basic machine. Right? You could just do a normal stress, and that's basically just collecting on a normal machine. You're just going to have to tilt the sample or the arms. But if you have that phi stage, you can really open up possibilities. And I think we're going to talk about the difference between the ISO inclination going over the top versus tilting it to the side. But, it kind of grows with your machine. So you can start basic, you can add components, and then you can even do more advanced.
Yeah, exactly. So now expanding this into the 2D space, you can see how if I have a 2D detector, what my coverage would look like. And if I'm doing an ISO inclination experiment, which is using the diffraction, the theta arms to simulate my sample tilt, we can see the orientation of the Debye rings here, as opposed to a side inclination experiment, which now your Debye rings are going to be oriented in that, we'll call it psi direction.
Yeah. And the thing I like about this method is it's about speed.
Yeah.
I mean, you are covering all kinds of inclinations at the same shot.
100%,
so, if you get lucky, man, you can do these measurements in 5 minutes.
Yeah. I mean, it's so easy to do in the software. And again, like if you have a template, you can just set up a sample, hit go, and you're good. Yeah.
Actually, where I like the other method, though, if you go back one slide, this method is, so you can see it's kind of centered on those dots, but it goes a little off to the side. And what this helps you do is, if you have pretty big grains. So you can, if you throw it at, like you have a 2D detector, sometimes you'll see these rings. And if they're perfectly uniform, that's a perfect sample of powder. But oftentimes they're a little bit sparkly. And that gives you that extra bit of sampling over a classic 1D. So I normally do this if it's got a little bit larger grain size. I do the ISO inclination if it's nice and uniform rings.
Yeah, again, because especially with the samples like rolled or textured samples, this could be definitely beneficial. So with that, I'm going to kind of close that out, and we're going to get to our analysis part.
All right, we're going to run this software live.
That's right.
So we're going to see.
Software is loaded. I've got no data imported in the software. There's nothing that's been pre-done. So this is all going to be done live.
And if anybody has any questions, by the way, make sure you type them in the YouTube window. Off to the right there, you've got the ability to type in questions. So go ahead and put them in there.
So this is our Leptos software package.
All right.
So this is used in a lot of different applications, and you can kind of see we have different modules here, but we're only interested today in that stress module. So I'm going to go ahead and open that up. And then I'm going to go ahead and import my data just by right-clicking. I can go ahead and select on my stress 1. This is the data that we're going to look at, just a simple 1D example, and if we have time, we'll get into 2D.
All right. So this is a tutorial. So if anybody wants to follow along or do the example, you can go ahead and do that in your files.
So you can see samples iron 211 with chrome radiation. It's labeled nicely. Okay, so the software picks up that we have plus and minus psi, right? And it's asking me if I want to aggregate that data in an intelligent manner so we can go ahead and calculate the shear stress.
All right, so when we collect the data with phi, you can either say, be at 0, and then you can collect the data at the different size, kind of start here, go all the way over the top.
Or rotate the sample.
Or you rotate the sample. And so this is saying, okay, we noticed that you had phi 0 and 180. You want me to put in a range.
Exactly.
All right.
So we're going to go ahead and say, yes, software, you are smart, and we're going to go ahead and take your advice.
It's all about the metadata.
So again, after I imported that data, it was just a raw file that that had all of our aggregated data from that job that we ran. And you can kind of see how it throws it all into the side. If you want to view everything separately, you can go ahead and do that. If you want to run through it, you can kind of see it shifting, right?
I see
as
the
I
peak
cycle
moving
through. Yeah. So that's a pretty good sign that we're going to be able to measure stress in this sample, right? Because we know our d-spacing's changing as a function of our sample orientation. So what I'm going to do is just switch these around, but before I do that, we'll just show you these different tabs here. Like all of our software, you can reorganize things depending on what you want and what's easier for you to see. In my case, I like to make 2 panels. So I'm just going to drag that up into 2 panels, and we're good. Now I got like a little side-by-side view.
All right. So on the left, what we're seeing is all of those scans superimposed, and so we can see this shift.
Exactly.
Right. So in the decrease of intensity, that actually comes from 2 things. One is from, just strain. I mean, it broadens the peak a little bit, but also it's penetration depth.
Exactly.
So that absorption effect.
Yeah. So that's one of the corrections. You can kind of, again, just cycling through, you can kind of see the data here taken at 0 and 90 degrees.
Okay, so just a basic data set was collected at phi 0 and then phi 90.
Yep. Now we're going to get into the fun stuff, though. So I'm just going to switch these 2 panels so our faces aren't blocking the view. All right, so to set up an actual analysis using that data that we just saw, we have a couple of options here. So we have some parameters for corrections and peak evaluation. So we're going to start with correction. So you can see the absorption. You can turn that on and off. Background you can turn on and off, or modulate the amount of data points at the edges of each frame that you want to be included into that background calculation. Very important to get an accurate background calculation to find the center of that peak.
All right.
Polarization, you can check or uncheck or check that. K-alpha-2 ratio, if you is typically half of K-alpha-1, right? If you're not using a monochromator, you want to leave that on. If you are, you can turn that off.
Yeah, and so the important thing to note here is that word monochromatic, because it can mean different things to different people.
Yes.
Right, so X-ray, and coming out of your X-ray tube, you're going to have kind of like white radiation. That's mostly taken out with energy discriminators these days. Then you got a K-beta and a K-alpha peak. So the K-beta, that's generally removed by like a filter, or again, you could even have like a Lynx IXCT, take that out electronically. Or you remove it with a mirror. Now, mirror, some people view a mirror as a monochromator because it does reduce to K-alpha. But the important distinguishing factor here is that it's K-alpha-1 and K-alpha-2 still. Right. So that right there says K-alpha-2 ratio. It's still going to be 0.5 with a mirror. Right? So like what kind of component would you have on the machine to change that number?
If you wanted to add like a crystal or something like that in front of the mirror.
Okay, so like a 2-bounce monochromator, they put that after the mirror. That's going to create that.
That would give you a pure K-alpha-1 beam.
All right.
You could do that, and then in that case, you would uncheck K-alpha-2.
All right.
And then we have some smoothing that we can do to help process the data, help us find that center peak, basically like a moving average.
Yeah, these peaks are generally pretty
broad,
right?
Can be noisy depending on what your data collection time is.
And that's something to think about too when you were planning, right? You don't have to collect this every 0.01 degrees. Generally 0.05 degrees.
Because the peaks are so broad.
And use a longer dwell time on that stuff.
Definitely recommend doing that. Yeah, that's good advice. So in our case, you can kind of see we're going to select the material that we're looking at, right? For the analysis. We have a database that's built into the software that I'm just going to open up briefly. So you can see it's tabulated with all these different crystal orientations of these different materials because the elastic constants are not necessarily the same in all different crystal all the different crystal reflections, right? So typically a single crystal we consider anisotropic, right? So we have to think about that when we're talking about looking at materials on this length scale.
All right, so we got these so you got a material, we understand that, right? Like magnesium, aluminum, all these different materials. Then you got HKL. So that means something about like the direction of the unit cell, right?
Exactly.
Okay, so that's like the different plane of the unit cell. And then you got wavelength.
Wavelength of the radiation that you're using, you can see we have a selection.
Okay.
Right, because that's going to change the location of said reflection.
All right, and then 2 theta would be
that's calculated, based on the wavelength. And you can kind of see these 2 different elastic constant, Young's modulus and Poisson's ratio.
Okay.
Those are going to be used to calculate stresses from strain. essentially.
So Poisson ratio, that kind of is telling us about how stress in one direction
can affect the elongation in another direction.
Yeah, affects another. I mean, sometimes we make the assumption that it's a volume conservation process. That's not always the case.
No.
And then Young's modulus, the higher the number, the stiffer the material.
Yep, exactly.
Okay.
Yeah, so like you said, ceramics, typically very high stiffness compared to like a metal or something like that, right?
And that's something that can be really hard. Like if anybody ever wants to practice, you know, the first thing they do is they grab their corundum standard, throw it in there, and then they measure it, and all of a sudden you get stressed, and it's like, oh, it's 5 megapascals, and oh no, this should be 0. Well, the reality is, first of all, that does have a little stress in it. But beyond that, it's that the Young modulus for a ceramic material is crazy high.
Yeah. So you can, you know, the strains that you're going to be measuring are probably a lot smaller.
Yeah, right? Tiny little strain gives you a huge amount of stress.
Yeah.
So actually, my recommendation, what I love to use, iron powder.
Yeah, loose iron powder gives you a really nice sanity check. Make sure you're getting 0.
Yep, get a nice loose iron powder. Put that into a sample holder. If you're going to tilt it, one thing I like to do is mix it with a little bit of like grease, like Vaseline or something like that. Put that in there, into the holder, make it nice and flat. And that's a great, you know, kind of sanity check on the 0 of the machine.
Yeah, 100%.
So, all right. So now, and then if you don't agree, I've had this before.
Yeah, go ahead.
You go on site and they're like, yo, Young's modulus for our company is this.
Yeah.
And it's like, okay, if that's what you want.
You can add your own.
You can add your own.
Yeah. So we're not going to, we won't judge you if you decide to add your own elastic constants for your situation. That's totally fine. And you can see these S1s and 1/2 S2. These are basically X-ray elastic constants that are calculated from those two. And the anisotropy factor, which can be used if you want to look at different crystal reflections.
Yeah.
So I'm just going to exit our database here. Go ahead and populate this with the correct parameters. In our case, we're looking at iron. The 211 reflection, I believe. We use chrome radiation, and you can see everything else is populated for me.
All right. All right. If it doesn't pop up, you go to the database and add your material.
Yep. It's that simple. And so now I have my sample material identified. We can take a look at these peak evaluation models that we have. So this is basically our peak fitting procedures that we can select from 5, right?
Yeah.
That's what our software gives you. So you have gravity, sliding gravity. If let's say you have like an asymmetric peak or something like that, and you want to just fit the peak above like a certain threshold of intensity, you can go ahead and do that with these two. We have an option for parabolic. I like the standard and Pearson 7 for like a pseudo-void, regular fitting function like that. But the rule of thumb is if you have good data, then you probably shouldn't, it doesn't matter what you use, right? You should get a consistent result.
Yeah, and the origin, a lot of that actually goes back to computers used to not be super fast.
Yeah.
And so the gravity type method's much faster to calculate.
Yeah. So I'm going to go ahead and I'm going to hit play, and I'm going to go ahead and select all of these. So it's going to do them all, and we'll see what happens.
So while you click that, maybe we can talk. Oh,
it's done. Yeah.
Well, I guess we'll have to talk about that later.
How do you like that?
All right.
I know. Well, so like we were just saying, this stuff is very fast these days.
It is. Yeah.
So you can go ahead and see that it went ahead and calculated the fitting on using all these different peak evaluation processes. It has these different stress models that came up. You can go ahead and just look at the linear regression here.
So what am I looking at there? What's
so
this
you're looking
graph?
at essentially the 2 theta, or in our case, we can go ahead and change this to strain or despacing.
Okay.
So now it's strain as a function of sine squared psi, and you can see it fits pretty closely to a line, right?
All right, so on this axis, we got the tilt angle. That's in sine squared. And then in this angle, we have the strain, or the elongation of the unit cell.
Right.
And if we plot it like that, what would we expect if we had 0 stress in the material?
You would just have a slope of 0.
Because it would be the same despacing no matter the tilt.
No strain, no stress.
Okay. And then the fact that it's kind of going downwards, what does that mean?
That implies that we have a residual stress in the material.
Okay. And would this be compressive? Or would this be tensile?
This
so
would be,
in the
well,
plane,
the slope is negative, right?
Yeah, so it means that the strain is smaller? Or no, the unit cell is smaller.
Yeah.
In the plane.
So it would be a compressive stress.
So it's compressive.
Yeah.
All right. And compressive, I mean, that's what you want, right?
Yeah.
If it was going up, that would be tensile.
Yeah.
So I remember once I went to this place where they were working on sinks. So, you have the little faucet, and everybody wants to have it nice and pretty, and, nickel coating, or, I think back then it was probably the gold color, right, that everybody wanted. And the problem was that the coating would fail, right? So it would start cracking, pretty quickly. And so they had to solve this, and what we did is then we measured it, and we found out, it's a tensile stress. I mean, from this deposition process, the temperature of the sink and all that during deposition, they were ending up with a tensile condition. And what that meant was that as the water cycled hot, cold, hot, cold, hot, cold, micro cracks formed, and they would just open up. The whole coating rips off, flakes, bam, bad coating. So what they did is then they adjusted those deposition parameters, right? I think they changed the temperature of the sink while they were depositing, and they were able to actually reverse the stress and make it so it was compressive. And what that meant that during that fatiguing, that constant cycling, hot, cold, hot, cold, hot, cold, microcrack forms, it just pushes it shut.
Yep.
So that's why, compressive versus tensile, very, very important. Fatigue, we always look for compressive.
Oh, yeah.
Right?
Big time.
All right, so we've got this line, and then from that,
so
what do we get?
Before I get into the line, I just want to kind of show you really quick all the processing.
Okay.
That's being done to the raw data. So you can see my original curve up here.
So it looks like it's not such a good fit then for that original curve, because it's the red line's on the left.
So you would think so. But what we're actually doing, remember, is taking out K alpha 2.
Oh, okay. And that's always on the right.
Yep. So you can see as it goes through all these different step-by-step refinement processes that once we do the K alpha 2 subtraction, we are now centered.
All right. All right.
Yep. And you can again play around with the background. If that doesn't look good to you, you can go ahead and change that if you're feeling up to it. And yeah, I mean that's pretty much the gist of all the fitting processes.
And if you look in there and you find, you know what, I got one that looks kind of not so good. Maybe we had a little bit of texture.
Right.
And peak was missing. So it gives you a point that's out. You can kind of turn some of them off.
You
right?
can. That's right. So if I just go ahead and click. Let's say I don't like that data point, it's going to go ahead and remove it. I don't know if you can see that over here because the data is so, close together. But yeah, just remove. You can go ahead and remove an outlier easily.
All right.
So again, if I look at, I'm going to plot normal and shear just because I can, because we have the data.
Okay.
Right? And you can kind of see it gives you a normal and shear scalar stress value of -520, and that's going to be megapascals.
Okay, so we're assuming that with normal, you're just assuming the stress is in the plane
That's
directly.
Right. Yep.
With the shear, it gives you the potential that the stress is a little inclinated.
Right, exactly. But you can see that's pretty close to zero relative to our normal stress.
Yeah. And graphically, we can see that too, right?
Right. So you would see, if you did have a shear stress, you would see size splitting, what we call size splitting, which is basically looks like an elliptical function that we would fit to.
Because if you looked at it, the same, kind of the analogous tilt this way or this way, it gives you a slightly different 2 theta or slightly different d, and so it's going to diverge those values on here, right?
Exactly.
Okay.
So if I cycle through all these different fits, you can see how the stress value...
I think we might be covering up that if we switch the windows here.
Good point, yes. I forgot. There we go. Okay. Yes, now we can see. So if I go ahead and just switch through these peak evaluation, or these different peak fits, you can see how that stress value is pretty darn close using any of them.
Yeah.
So that's gives me good confidence that we have good data.
Yeah, yeah. And then in the bottom, I see there's these different matrices that kind of correspond to that sigma 1,1.
Yeah, that's right. So these guys are only going to be useful if you have like a biaxial or like full biaxial shear tensor. And that's going to, again, give you the complete picture of the sample. And so, yeah, basically, I think in the 2D example, we'll be able to see that.
Okay.
But, yeah, so basically, these are your stresses, and this is kind of like your stress orientation matrix, which tells you how you have to rotate those stresses to be in line with the sample frame of reference, if that makes sense.
Yeah, yeah, and it also will give you the maximum stress.
Right.
So that is, if you make the assumption, for example, you have a little bit of shear in there, you make the assumption that it's in the plane, that's actually not the highest stress. The highest stress is a little inclinated, and the software is smart enough, automatically rotate that for you.
Yep.
Because that's what matters, right, is what is the maximum stress on the material.
Mm-hmm.
All right, so now that we have this.
So you can see, just really quick, I could do this at 0 and 90.
Okay,
right?
and it actually fits it all at the same time.
And look at
right?
how the stress changed in that direction.
Oh, wow.
Yeah, so.
All right, so now there's also then, we can kind of make a report out of this, right?
Yep. Yeah, so if we go ahead, if I can remember, there's like a little tailored report thing. Is it?
Print preview.
Yeah. Let me just go back.
Print report.
Is that it? Yeah.
I think so.
Let's see. There you go. Yep. Nice. We can try the extended. Print extended report. Oh, yeah.
It's always fun when
Nice.
I ask a question that was not anticipated.
That's right. Yeah. But yeah, you can kind of see how it throws everything onto a nice Word document for you.
Yeah, and there's a nice editor in the background where right under that same field you can change your logo, put your company logo up there, put the information that'll display.
Yep.
So a nice way to make a report. All right, again, if anybody has any questions, let's make sure to type them in. Looks like we have quite a few questions coming in so far, so keep them coming. But you had said that we have another example.
We do, yeah. So if I go ahead and let's try a 2D example.
All right.
Go ahead and hit new stress.
And this episode is getting a little bit longer, but we do want to make sure to go over this. This is really kind of cool stuff. So if you have to go, you can always come back, watch it on our YouTube channel. And also you can send the questions in. We have an email address. It is live.events@brooker.com. So if we don't get to your question, or you have that question later on, go ahead, send it in there. All right, so it looks like you just imported the data.
Very easy.
All right, and it came in.
Yep, it came in. You can see we have 7 frames.
Okay. And we see that little like debuy ring going on there.
Yep, so I'm going to go ahead and just change the contrast a little bit so we can see it better.
Yep.
And then you can just use this cursor to fit, get some background in there. Okay, let's see. I'm going to expand that a little bit. And you can see it's changing the numbers here in the integration as I do that. So you can fine tune that if you want after.
And this example looks like it's kind of got the round detector, so from like a Vantech
Yep, exactly.
500. Yeah. But if you had an Eiger, it would just kind of bring it in that full square version.
So now you can see I'm pretty happy with that.
Yep.
And you can see it's automatically, because based on the frame, right, it pulls in all this information.
Okay. Yep.
And these can be important. So this is basically going to divvy up how we do the integration. Right?
Okay. So if it's really spotty, you make the
numbers a little smaller.
The subgroups a little smaller.
Exactly.
Okay.
All right, so I'm just going to pull in the same material here.
And while you're doing that too, one thing I really like here is the peak rejection area. What that does is if you do have a spotty debuy ring, you can set that so if the peak is below a certain threshold, it'll actually not use that data.
Yep.
So, that helps to deal with that condition.
All right, so I think I have everything in here to my satisfaction. I'm going to go ahead and hit play. And there you go.
All right.
It's that easy. It's that quick.
So in the upper left, we have the debuy ring, and it's kind of hard to see it here, but there's a bunch of little X's on it.
Yeah, that correlates to these line patterns here.
Yeah, so it's fitting it. And then the red line on the right,
I can scroll.
That is actually a simulation of the debuy ring, and the X's are the data points. And then the black line would be a stress-free sample.
Yep. So you can see the integration that's being done here. So like if I wanted to make this a little less noisy, I could reduce the amount of subregions. Let's just see what that looks like. Oh, you can see it didn't take my... There we go. Okay, let's see.
Yep, there you go. So that's more data going to each data point.
Yep.
Right?
And you have kind of have the same parameters like you do in the 1D example, but we have in this case is a lot more data, right? So I can go ahead and go normal and shear, but then I can also go biaxial and then biaxial with shear. And you can see how it now populates the stress orientation matrix as well as our stress tensor.
Yeah, so in the upper right of that result area, what we're seeing is the raw matrix, but then on the left side, that's that reoriented matrix. So that's giving you your principal stresses.
Yep. And That also gives you an option to go triaxial, but like we said, if you don't know, the stress in the z direction, which is probably 0, right?
Yeah.
Through assumption, then you would need the stress-free d-spacing to get that.
Yeah, I mean, in a classic material, if the stress on the surface pointing out is not 0, the surface doesn't exist, right? I mean, it's going to blow up.
Yep, exactly.
But, kinetically limited regimes these days with growth and that, you never know.
Yeah.
And another neat thing you can do, too, is now that you have that three-dimensional, you can actually view it three-dimensionally.
Yes. Right? So if we go to the ellipsoid, you can see, if I reorient this, how those stresses appear.
So the blue arrows pointing in would mean it's compressive, right, in the plane. But when you tilted it down, we could actually see it was slightly oriented relative.
Yep.
And that can actually come from two things. One would be that the stress is actually a little out of the plane. The other thing actually that you get, especially if you have curved surfaces, is that it might just be that when you mounted it, it wasn't perfectly flat.
Right.
Like you were hitting off to the side of the curve a little bit. So, and the nice thing about 2D, though, is how much quicker this measurement is, and then the analysis.
Yeah.
It's really fast. The other thing is it uses a little bit more general algorithm. So there's that classic sine squared psi algorithm that's used for the 1D analysis we talked about.
Right.
Here, it's actually using the diffraction vector approach developed by Bob He. You can read a lot about it in the book, Introduction to Two-Dimensional Diffraction. Right. But it's a more general concept to stress analysis with XRD.
Yep.
So a lot more details in there. So that is now stress. Now there are other things that we could do here. We could do, it's called multi-HKL method. That's where you can actually just do a normal theta 2 theta scan. It uses the fact that the diffraction vector changes an angle. It uses multiple HKLs. That's useful for like GID stress, things like that. That's all built in here.
Yeah, it is. So. Or the grazing incidence, if you want to get like a depth profile.
Yeah, and that's really neat is if you take a series of those GID scans, you can actually see the stress as a function of depth in the material. All right, so let's get to some of these questions that have come in. So again, if you have a question that pops up in your mind, type it in the right side. Otherwise, send it to live.events@brooker.com, and we will answer that after. So from JF, hi from Germany, I'm doing residual stress measurements on new titanium alloys, additively manufactured.
Ooh, nice.
That's very interesting. We don't have a Eulerian cradle, so I'm simulating the side tilt by offset coupled to theta. For the right phi angle, I constructed a sample holder, 0.4590. How long should a measurement be for each phi angle? For example, 11 measurement points. So how long do you collect?
That's a great question. It's going to depend on, what source you're using, right? It's going to depend on a number of factors. I normally go by when does the data not look noisy?
Yeah, that's and that the thing to think about too is it's not just when does it not look noisy in the one measurement, but you kind of want to do a quick measurement, see what your statistics look like.
Exactly.
Be able to differentiate that peak nicely.
Yep.
So titanium, generally you're probably going to be looking at copper
I would
radiation,
say,
and then pick that high angle peak. Like you said there, do the 0.4590, and I mean off the cuff, I would probably say a few minutes.
Yeah, I mean, it doesn't normally take that long to do these types of measurements.
All right. Then from Gopal, the question is, how make the method?
So again, you just kind of go into our software, and the wizard walks you through all the different steps.
Yep. So here we use that mantra: plan, measure, analyze. For the planning, go into Commander, and then in there you're going to have a tab called Wizard. File new, stress, and that'll walk you right through it. Also, if anybody ever wants additional training on that stuff, we have a lot of training opportunities. At Brooker, you have classes, so you can actually come to our facilities, take a class. We also do digital trainings, so you can schedule one of those and connect with one of our app scientists remotely. And we have video and all of that nice stuff so that we can help you out directly on your specific problem. And then another option is that you can always schedule for somebody to come out and work on your machine with your specific problem on site.
I think we have a couple of 2D classes scheduled this year.
Yeah,
we could
yeah, here in
probably-
Madison, and then there's also some in Karlsruhe
Yeah.
and some of our other application labs internationally. But I do have to say, the digital training has really, really been something that people are excited about. And normally you can just get right to the problem.
Yeah.
And they're pretty inexpensive too. All right, another question from JF. If there is no slope, so no stress, but there is a size splitting, what does this mean?
I've never seen that before. So, I mean, to me, that means that your sample's probably not flat, maybe.
Well,
but I'm not sure.
Yeah, if we think about it, that means that, so there's no slope, so that means that the middle direction are going to get no stress, but it has all shear. So it would mean, I guess, that it's a pure shear.
Yeah.
It's a pure shear. Because in the plane, you have a lattice parameter going this way and another one going this way. Huh?
Right.
So that would be a little bit odd. You'd have to have some sort of maybe a gradient, temperature gradient or something like that in the sample. Maybe would do that.
Yeah.
Or if you're not hitting the same spot on the sample during the measurement. All right, from Aquila. Hello, if we want to measure stress at high temperatures, how can we differ between peak shift by stress and by thermal expansion? We need to cool back to room temperature before the measurement.
I think that with thermal expansion, you're generally going to have a consistent, right? I mean, if you think about that, your stress is going to, your expansion is going to be similar in all directions, I think, right? So wouldn't that be more of a hydrostatic stress?
So that's going to change the lattice parameter.
Right.
And
uniformly.
Yeah, generally in XRD, what we're assuming is that the only change of the lattice parameter vertically is due to the Poisson effect. So I think what the answer, like in terms of what you have to do to get the result out, is unfortunately, we don't take that into account with the software, a change of temperature.
Right.
So you'd have to go back to the sine squared psi equation. And then when you calculate your strain, so strain is delta D over D. You have to use the right Ds.
Right.
Right? Now, actually, now that I'm thinking about it, though, what you could do is this. You could go in to the database and just put a different entry in for each of the temperatures and with the different 2 theta. Because that 2 theta is the assumed D space.
Right.
So you could just go in there, iron 211 at room temp, iron 211 at 100.
Yeah, that's a great point. So you could just go into the software and change the actual angle, right?
Yeah.
The relative angle, and then, at that, whatever that temperature would be, measure the D-spacing of the stress-free sample.
Yeah, and that'll give you, that'll allow you to use the software to actually calculate the stress at each
Yeah, it's a good
value.
question. Great question.
All right, another question from Aquila. Can we measure stress of coatings in grazing incidents?
The answer is yes. So what you would do essentially is instead of, it would be more of the multiple HKL method, basically. That's all you would be doing. So you'd have a fixed incoming angle, and you would just sweep in 2 theta. So just sweep your detector, and hopefully you have enough peaks to get, a good reliable result. But essentially, right, you're changing the diffraction vector.
Yeah. So the diffraction vector is the bisection of the incident outgoing angle. We have the incident angle fixed. This one is coming up and over. That's going to change that diffraction vector during the scan. And in the software, all you got to do then is make sure that you have the different HKLs typed in with their peak locations. It'll take care of it. So, all right. And actually, we got some questions that had come in before, so we're going to go to that. And then we'll come back to the ones, too, that are in YouTube. So from Susan, I have a heavily textured material. Can I use this method?
It's going to be very difficult. Especially if you're using a 1D approach. So, I mean, again, we're making the assumption that we have these infinite strain gauges, right? So to have that, you have to have randomly oriented crystallites.
If you don't have the peak locations, then all of a sudden that sine squared plot, you're going to have some missing spots, or you're going to have inaccurately positioned spots. So generally, actually, they would say for residual stress, you shouldn't have any texture. And what I found is that with the 2D method, because it's modeling the whole device here, it's a little bit more robust.
Yeah, definitely.
So you have a better potential. But if you're looking at something pretty strongly oriented, like a copper film that you deposited, man, that's a tricky one.
It's going to be a challenge.
That's right. And in fact, we have had some questions where people say, hey, I want to do residual stress, but I want to do it on an epitaxial film. Well, you just have to go back to fundamentals then and say, you don't need stress, you just measure the lattice parameter.
Yeah, exactly.
And now you get the strain. All right. So another question from YouTube here is from Victoria. She's one of our users actually up in Canada.
Oh, nice.
So hello, Victoria. You mentioned that you can remove data points, outliers. Is this a new feature in Leptos 7.14?
Oof, that's a good question. I'm going to defer to you on that one.
They were bugging me before, telling me I was the old man who always tells the stories. You know, I think that's been there, actually, since version 7, for sure. I think it may have even been there before. So, although the thing is, if you're doing 2D, I don't think that function is there, right? So if we look at your laptop right now,
let's see.
and you go to 2D.
Right here?
Yeah, go to the calculation.
Oh, gotcha.
Here.
Yeah.
Here you can't turn them off.
No, but we do have that peak rejection thing over here.
It's been there, but it's only available for the kind of the 1D scan modes. What you can do if you want to use it is you could always take your 2D data, manually reduce it to 1D, so integrate it out, and then bring it in.
Yeah.
And now you could use that, or you use that peak rejection thing. Because generally, if you have the good signal to background, then the peak is going to be good.
And you can see there's an option to integrate to 1D.
Yeah.
Pretty easy.
All right, from Akshay, and a lot of good questions coming in. Keep them going.
Yeah, a lot of
like I
good
said, we're going to
questions.
answer them. It's going to get a little bit long. If anybody wants to tune in later again, you can check the whole video on YouTube. So from Akshay, hi, what does it mean if we get different stress values and different curve fitting techniques, which varies more than 100 megapascals? So they use the different fit methods, and they get a different value.
You probably have something going on with your peak shapes.
Yeah.
Or like, so I would cycle through all of the data like we did over here and just see exactly what's going on with my fit. Am I getting some abnormalities that's due to like maybe some noise or something like that? Maybe my background isn't fitting properly, or if I don't have enough background on both sides, right?
Or you have peak convolution.
Right. That
You
could
have
also
another
be
peak
another
going
thing.
in on there.
So one way to battle that
yeah.
would be to use the gravity or sliding gravity.
Yep. Also, maybe
approach.
find a different reflection.
Yeah, that could also help in your measurement.
Or make sure that you're measuring that higher angle reflection. So
yeah.
Another view I like to look at is actually if you go up to the regular stress node.
Yeah.
And then you see the multi, where you get all the plots. I think it's the second tab.
Oh, the merge plot. Yeah, the data set. Yep.
This data set, I like to look at that one too. This gives you an idea. If you see anything funky going on, that's going to tell you that's where your issue is coming from. Can you suggest suppliers who supply stress-free iron powder? Unfortunately not. I mean, the stuff I've used, I think, was from Sigma.
Alpha, Acer,
or Alpha.
Yeah, something like that.
Yeah.
Like APS 6 to 10 microns, something like that.
Yep.
Yeah.
Look for a nice, smaller micron size, and there's always the question if generally I think they're made by like a thermal spray process, so they're stress free. But yeah, if they're cooled too rapidly, something like this, you could have a problem.
Like gas atomization or something.
Yeah. I mean, if it's like quenched, I could imagine it would change lattice parameter. But when I've done it with those powders, it's been pretty good. I'm not aware of anybody who does a certified one though. So. All right, also from Akshay, when you use a 2D detector instead of 1D detector for the same data quality, how much will be reduction in the measurement time? All right, so let's assume that we have a nice sample, powder-like ring, so we can do ISO. Inclination, which is side, or not ISO, but side inclination, right, with the 2D.
Yeah.
What do you think? What's our time saving?
I don't know a number off the top of my head, right? Because every situation is going to be different. But, I mean, you can see right here, we're looking at, this gives you 5 data points as opposed to like 1 data point,
Yep.
right?
Yeah, for me, that's been about the factor.
Yeah.
About a factor of 5. And where this becomes really useful too is there's another function in Leptos where you can actually do stress mapping. So,
Right.
like I took a razor blade, and then we actually mapped the stress all along the razor blade. It's really neat, actually. It's a cool exercise if anybody wants to do it. Because where it's cut out, sometimes you're going to see a different stress near that. And then also near the edge, you might see a stress. And with that, doing it with the 1D method, that takes forever. You might be talking 30 minutes per spot. No, it's not too bad, but if you're doing 100 spots, that's a lot.
Yeah.
Generally, we're talking like 5-6 minutes doing it per point for the full biaxial with shear.
Yeah.
All right, from JF, how does the software calculate the hydrostatic stress?
Hydrostatic?
Hydrostatic stress.
I can refer you to the Leptos manual, and it's all in there.
I believe it's actually deviation.
Yeah, right.
From
the deviation
the
tensor?
expected 2 theta. So, and I believe it calculates it only with the triaxial.
Right.
If you do it. So what it's doing is it's looking at that assumption that you should have 0 stress pointing out of the sample. And that assumption is not that a measurement out of the sample gives you the correct d-spacing, because we would expect a shift due to Poisson ratio.
Yeah.
But if it deviates from that expectation, that's where the hydrostatic stress comes in. All right, is Bragg 2D in Lynx Eye available for the analysis of residual stress?
Lynx Eye and
Bragg 2D. So
yeah.
Bragg 2D, no, you're not going to get a benefit from it because you're going to have to scan. Where Bragg 2D comes in is it's really good for assessing, say, the sample preparation quality. If it's spotty Debye rings versus not spotty. Also, if you have some orientation, it can help to identify that issues. But in the case of residual stress, you get the big 2D benefit from having a pixelated detector. So if you have a Vantec 500, if you have an Eiger, then you get that big pixelated detector. That's where you're going to see the benefit. So I'd recommend with that Lynx Eye is to use it in 1D mode and try to do snapshots. Bam, bam, bam.
Yep.
That's really going to speed things up. All right, from Quang Ho, is cobalt K alpha radiation suitable for residual stress also?
Absolutely.
All depends on the material.
Well, if you're looking at iron, it's a good one because it avoids the fluorescence and it gives you decent penetration depth.
Yep. It doesn't shift though that 211 as much.
Yeah. So you maybe look at like a higher order reflection, but it's similar radiation to copper, so that's why it's like a good middle ground. Wavelength wise to copper. I mean. Yeah.
Generally what I do is I look for any ASTM standard.
Yeah.
Look what they're recommending, and then I'll go to in EVA. Diffract EVA, there's a tool called AbsorbX. And that software, you can type in the angle, the material, the radiation, you can get an idea of the penetration depth. And we want to have a decent sampling.
Yeah.
So look at that effect too, penetration depth. And then lastly, check those peak locations. We want to get as high as you can. Yeah. When I say high, I mean like, you look at the machine and you're scared.
Yeah, that the source is going to hit the detector.
You're like watching it and they're like, almost touching. You want to get as high as you can.
Yeah.
And, generally, 160, 150, that's going to be your top out when they get really close. So, check, with cobalt, those things, and your material, and see if it's suitable. All right. We have an answer from one of our app scientists actually in Germany, Kurt. So, hello, JF. If you have a stress-free sample and still obtain a size splitting, it could also arise from either a sample alignment error or a slight offset of the incident beam. So,
makes sense.
Yeah, and one of the things that's really useful, if you dig through the cabinet of things, right? Every machine has the cabinet of things.
Yeah.
Sometimes you'll find a sample that's a fluorescent sample. So it's either going to be a metal puck with like this white coating to it, or it'll be just a white piece of paper with kind of orange peel, glowy, shiny coating. Take that, put it in your machine, and look at the beam. And then move the machine, just like you would in the measurement, and does the beam move?
Yeah, that's a very important thing, and that's one of the reasons that side inclination,
that's right,
when you're running 2D, can be beneficial.
Yeah. So, check that out. Now, we've got a few other questions that came in from Adam. I work with exotic alloys. Where can I find the modulus and Poisson ratio?
It's a great question. If it's a novel alloy, you can probably get it through some other means. But if there's like research that's been done on the material, they have tabulated moduli and like Poisson's ratio. You could probably get it by looking at references online and things like that.
Yeah, the best
like
thing,
journals and
do a literature search,
yeah.
or find a collaborator who can do theoretical calculations of the moduli.
Right.
So oftentimes a lot of these packages, these thermodynamic calculations and kinetic packages, they can actually calculate your moduli as a function of
alloy composition and structure.
Yeah. From Roger, we have, what is the largest sample that can be measured?
Take your engine block out of your car.
I got a V8 from my Mustang.
Throw it right on
I
onto
want to
your
measure
stage.
it in there, huh?
Tilt it. You'll be. It's no problem. Yeah.
What is the largest?
The largest depends on the stage that you have. So I think our stages we can go up to like what 5 kilograms.
Yep.
Yeah. So you could get one of those. If you're running an ISO inclination, you don't have to tilt it, which is useful, right? Yep. If you have to tilt a big sample, then it can be a little nerve-wracking. And then you're not taking the stress out of your stress.
That's right. Probably the biggest thing that I've seen measured in terms of just dimensionality was actually a camshaft.
Yeah.
So we had a camshaft from an engine, and what we did is we actually removed the stage entirely. Just click it out with the bayonet. We put a little lab jack in the middle, turn it up to the right height, and then we stuck the camshaft right through the center of the goniometer.
Mm-hmm.
And we were able to measure the stress on the cam lobes.
Yeah.
So one thing to be wary of, by the way, if you have to cut your sample, you have to cut it really far away from the area you want to measure the stress.
Because then you're going to change the stress state.
That's right, and you have to cool it when you're cutting so that you don't affect that stress state.
Yeah. You can get creative, though.
Now, kind of another question. What is the smallest sample? What's the smallest thing you've measured?
The smallest thing that I've measured, I'd probably use like a millimeter collimator on a, so not super small. You can get even smaller than that. It's really going to come down to how big can your beam be on the sample, or how little can your beam be on the sample.
So for me, it was a tiny spring. So imagine, you take your pen apart, you take the pen, take the end out, and there's that little spring, and they wanted to measure the stress right on the edge of that spring. So that we had to use, really tight collimator. I think we were going like 50 micron and hit the stress. But the saving grace of that measurement was that in leptos, it automatically rotates the matrix. So even though we missed, say, the exact tip of the spring, we were off to the side a little bit, we could still get the stress measurement, even though we were a little bit off. All right. And then one more question here we have that came in from Abdel. How to measure residual stress in thin films?
How thin?
Yeah, I guess. Well, I would say we got two types of thin film. We got something I like to refer to as a coating, something like a chrome on a bumper, something like that. Generally 100 microns, maybe 50 microns.
Yeah.
Randomly oriented.
Yeah. So
what do you think?
So you would just apply this method.
Normal method, right?
Yeah.
Now, what if we get down to, say, a micron or less, but still randomly oriented?
That you would probably want to use like maybe a grazing incidence approach, maybe.
Yeah. So
as you start to get down to those nanometer level measurements.
Yeah, like we talked about before, GID, multi-HKL approach. So I measure the GID in the software. Check out the tutorial. There's a great example of it, multi-HKL.
Yep.
And now, what if you got
epitaxial?
Epi films.
Oh, those are great. So that, you're just going to be looking at relative peak positions between the substrate and the film.
Less about stress, more about strain.
Yep.
So, and strain engineering is huge for epi films, right? So, but there, what we do is just measure the lattice parameters. So, and you'll be good to go. So if any other questions come up, let's make sure to send them in to live.events@brooker.com. Otherwise, thank you, everybody, for joining. And thank you, Jonathan.
Yep. Thank you guys for having me on today.
Yeah,
really
all the great information. And until next time, keep your signal high and your background low.